Yes, Murthy.
Ma'am, was it audible, ma'am? Was the
Yes,
audio clear?
yes, 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 yes.
Yeah, thank you, ma'am. So this was the demonstration.
What is the PBX?
This was the demonstration for the Open BTS. Now we'll check on another cell phone emulation tool such as SRS LTE. The SRS LTE is also a 4G emulation toolkit which implements a typical 4G LTE protocol stack in a software. It basically includes all the components that is required for in order to have a complete 4G system setup, and it basically operates on the band LTE band 7 frequency, and is most widely operated at frequencies such as 2.5 gigahertz to 2.6 gigahertz range. And the typical architecture of the SRS LTE is as illustrated in the image. We have an SRS EPC, which is a core network that runs on an individual system. Then we will be having a SRS eNode B, which acts as a base station, which also runs on another individual system. Then we will be having a user equipment, which is a cell phone, which gets connected to the base station. The core network includes all the components required, such as the HSS, home subscriber service, uh, home subscriber service, which contains the information of the user subscriber information. Then we have the gateway servers such as switching gateway and a packet gateway. Then we have the mobility management entity, which is responsible for the connection management and bearer management. The communication between the core network and the base station happens with the mobility management entity and serving gateway with the help of S1 interface. So the SRSLT demo setup with the help of a USRP hardware and a user equipment cell phone looks like this. Like here, a SRS core network SRS EPC will be run on a Linux system on a individual system, and SRS eNode B will be run on another system. So this eNode B acts as a base station which makes use of a USRP in order to transmit the signal, transmit and receive. Then the user equipment will be a cell phone, a 4G cell phone, which connects to the base station, and in order to have a traffic exchange. And the multiple systems will be connected with each other with the help of a switch or network connection. So this is the setup of a 4G setup with the help of SRSLT and a USRP driver, USRP hardware looks, and this is the small demonstration of the SRSLT. Once again. Is it audible this time?
Just remember to set the USB to 3.1 if you wish. Use the.
Hello.
Yes, yes, it is audible, Murthy.
Sorry. Okay.
Yes. Check it again. Actually, initially we were getting, now it is not.
Oh, ma'am, it's not audible, ma'am.
Mhm.
1 second, ma'am. I'll just check. Ma'am, give me 1 minute, ma'am.
Okay, okay, no problem.
Ma'am, now I'll play this video.
I just want to show off something that's really neat about the SRS
Yes,
LTE.
it is.
The way we can graph how RF is working. It's a Docker container just to control all the using these do several projects. You know, if one.
Ma'am, was it audible, ma'am? Hello?
Yes, yes, it was audible. It was audible.
Thank you, ma'am. Thank you.
Please continue.
Something that's really neat. This can share a graph from if it's I'm going to just all the different custom libraries. It's easy thing to use. Several projects. You know, if one needs UHD, blah, different one, something else. So it's good to keep them separate. Not have to reinstall. But start there. And then I have another shell connected. Execute that, and yet another one. So this one I'll start. I got the masquerade. PC. This one we will start the node B. That's here somewhere in this. Okay, node B set up graphic. It comes out and displays this neat thing I will show off. But then I'll take the handset, which has a symbol in here that's in the and if we're lucky, at some point we will get the connect here. And to do that, I need to turn something on. There we go. Turn on the auxiliary equipment and it connected, and we allocated 172.16.0.0.0. So at this point, I'm going to run as a server container. This is really bad focus. And then on the should run something called Magic Eye. And this the client. Since we start here, we're going to start uploading up to date is it still? Do is put it in airplane mode. Airplane mode. It connects. There we go. 4G. Now we can start now. This this as I move. Says I move. F sniffer. This is the uplink. And see it's going fuzzy now. Get it in just the right place. So here's a there's a good spot there. There we go. 15 megabits a second. As you're moving around, any signal, figure this is on band 20, no, band 7, 26. 26. Figure out what that wavelength is. A quarter of that distance. So it's really neat. You find where good spots are. Anyway, I just wanted to show that off. I perf right on the phone. Sending jobs of data to the server container around the room and see how good it is.
This was the demonstration in which the SRSLD was used as a base station, and a UE was used in order to have a traffic exchange between the base station and the mobile. So now we will check on another open source like a toolkit for 4G as well as 5G emulation, such as Open Air Interface 5G, which is developed by Eurocom. And this open Air Interface 5G implements both 4G network as well as 5G network implementation. And when it comes to the 5G network implementation, Open Air Interface has two types of architectures. One is the non-standalone deployment mode, and another is the standalone deployment mode. When it comes to non-standalone operation, Open Air Interface 5G makes use of a 4G network in order to have a signaling information exchange, and a 5G network in order to have data exchange, and a common EPC or a common core network handles both the E node B as well as the G node B, E node B for the 4G section and G node B for the 5G section. So there will be two base stations which will be synchronized together, and both of the 4G as well as 5G base stations will be controlled by a common core network when it comes to the non-standalone setup for the 5G set, for the open interface 5G. When it comes to the standalone setup, we have a dedicated 5G RAN, which implements all the 5G network capabilities in order to have in order to establish in order to enable a 5G system, in order to enable a 5G base station setup. And this 5G base station is handled by a access and mobility management function, which handles complete 5G operation in a standalone mode. When it for the non-standalone setup, with the help of a USRP, the typical non-standalone setup looks like this. Here, there is a EPC server which is run on an individual PC on a Linux system. like example Linux 16.04 operating system. Then we have a G node B which is run on another system. Then we have E node B which is run on another system. This E node B and B node B are connected, are mixes of USRPs. So like a USRP B210 is connected for the G node B as well as E node B, and these two USRPs have been synchronized together with the help of a octoclock clock module, uh, and a UE such as a 5G cell phone such as Google Pixel or Google Pixel can be made use, and these two base stations communicate with each other with the help of an X2 interface, and this is how the this is how the non-standalone setup for an open interface 5G it looks like, and we'll check on the demonstration for the open interface 5G.
Hello, my name is Florian Kaltenberger. I'm an assistant professor here at Eurocom, and today I would like to show you our 5GNR non-standalone test bench. The setup here actually combines multiple test benches in one. We have a USB N310 up there, we have an X310 here, but the ones we're going to use for the demo right now are actually these two B210s down here, where one of them, the right one here, serves as the E node B. So this one is operating in Band 7, and you can see you have the duplexer.
Ma'am, is it audio audible, ma'am?
Yes, Murthy, it's very clear.
Okay, thank you.
Here for Band 7, and the other B210 serves as the front end for the G node B. This is operating in TDD, and at the moment we don't have a dedicated front end for it, so we simply use two antennas, one for TX and RX. Both of the USRPs are connected to antennas here in this Faraday cage, where I also have the phone that we're going to use, which is an Oppo Reno 5G. So let's go and get started. First we're going to launch the E node B from using this command line here. Okay, E node B is running. And then we're going to launch the G node B from this window here. Okay, we can see it's running too. Both USRPs are transmitting and receiving, as you can see here. And now we're going to wake up the phone from airplane mode. And we can see up here that 5G connection. Okay, now that the phone is connected to the 5G network, let's see if we can send some pings. Yes, we can. And we can also try and send some iPerf traffic. Alright, so now I've started the Wireshark application here on the phone. Okay, and I'm going to stop the ping and launch an iPerf here on the screen. And we can see here that the traffic is being received at the phone. Okay, at the moment the throughput is not very high, but we're working on that. And that completes the demo. Thank you for watching.
This was the demonstration for the Open Interface 5G, in which E Node B and G Node B, the 4G as well as the 5G base station was interacting with the user equipment, in which the signaling operation was handled by E Node B, and the data operation is handled by the G Node B, and traffic information has been exchanged between the user equipment as well as the base stations. And here the non-standalone setup is operated at a frequency range which is FR1 at 3.5 gigahertz range. So this was the a demonstration for on the open interface 5G, and these were the some of the few open source tools that we have included. And yeah, thank you very much. Thank you, everyone.
Yes, thank you very much, Murthy.
Thank you.
If any participant has any questions, they can ask him. I request Murthy to please put your mail ID in the chat box.
Sure, ma'am.
For any other queries, they can contact you in future.
Sure, ma'am.
I think Anushka madam has some query. Yes, ma'am. Hello.
Ma'am?
No, ma'am. I'm not having any query.
Your mic
Thank
was unmuted, so I thought.
No, ma'am. Sorry.
Okay. Murthy, please give us your mail ID. Put it in the chat box.
Yes, ma'am. I have given my mail ID in the chat box.
Okay. Thank you so much.
Yeah, thank you, ma'am. Thank you, everyone.
Has Raghavendra joined?
Yeah, I'll inform him to join.
Yes, ma'am. I'm here.
Yeah, he is there, I think. Yes, Raghavendra, please.
Yeah. Okay.
Thank you, Murthy. Thank you so much.
Yes, ma'am.
Right. Okay. Good afternoon, everyone. It's Raghavendra. Right now, as promised in the morning, I'll be giving a very brief as to how we've right now implemented the physical layer portion of a VLC system, where VLC stands for Visible Light Communication. So basically, in this system, we take up an LED. We encode all our information in the LED by making it blink. We then have a photodiode receiver through which we receive the actual signal, and then we're able to actually decode it to get our message. Similar to what I showed you with, and Ajay would have also showed you. In fact, he's also here. The setup is with Ajay. So once I'm done with the brief intro, he'll be giving you a demonstration, or rather he'll be running the code and showing it to you. Either he or I will then run the commentary on actually what is happening, post which I'll also show you the exact way that we've coded, the exact blocks that we've included. We've actually derived all of this from the previous frameworks that we've had from the CISO framework. So I'll tell you exactly how and why we've derived certain blocks from that and what additional blocks we've put in over there. Now, and post that, if we have a little bit of time, I'll also tell you something about something called as Open VLC. So this is a proper communication stack that is not just the physical layer, but goes up to the network and the MAC layer as well. We've yet to implement this, but OpenVNC is actually a concept that was done by a university in Spain. They have a website about it, and we're actually trying to replicate that right now. So before I go there, I'll just explain to you how our system works, post which, if we have time, I'll tell you about OpenVLC as well. Okay. Now, again, I won't take too much time on the theory. I know you've all heard a lot of theory. So I'll just take a very little amount of time to explain to you how exactly we do it. Now, in the VLC system, obviously, this is not the same as your whatever CISO OFDM MIMO we showed, because the fundamental difference is that over there, we were using radio waves, which were in the range of 900 megahertz to 6 gigahertz. Somewhere within that, we were doing it. But right now, when we go to when we go to actually visible light communication, there are a couple of aspects that we will have to include to that. First, I'll go with the hardware aspects. First, actually, I'll address why VLC. What is so special about VLC? Why do we need something called as visual light system? Post which, I'll also tell you the hardware differences that we had to implement, and then the software differences. And then we'll show you the demonstration. Now, firstly, VLC, as it said, visible light communication has a couple of advantages over your normal radio signals. First of all, your visible light range, which is in the terms of nanohertz, has actually a larger bandwidth when you compare it to your the rest of the signals that we use to transmit right now. So right now we try to go from anywhere between megahertz like FM, which is on the lower range, to your gigahertz. One of the 5G bands is around 3 or 3.3 gigahertz. So this is the band that we actually have our transmitters in. Like I said, NI-USRPs aren't able to transmit more than 6 gigahertz. So this severely limits our bandwidth, especially when it comes to prototyping. Of course, there are 5G systems that are there, but like Vinipal sir explained in the morning, these are not tinkerable as such, or rather, it's very difficult to find hardware that will allow you to transmit in these frequencies. So in that case, when you are losing spectrum, you can actually go to a point where you say, okay, fine, I will, in order to get around this, I'll not use radio waves at all. I'll go to the visual spectrum of things. Now, the second thing is radio waves, as you might know, like if you keep your phone inside your house, you would obviously get some amount of signal from your base station, right? Unless you are in a place that is completely covered by metal, you will actually, the radio waves actually are able to penetrate walls. They are able to fit in through small gaps, etc. It's a good thing when you're talking about this when you want signal to penetrate places, but let's say you have some issues with respect to security or signal security or your information security. Let's say you want to confine all of your signal in a room. Now, if you want to do that with a radio signal, firstly, in normal rooms, that's not possible. It'll obviously leak out a little bit. So your security won't be there. And if you want to do it, you'll actually have to do a lot of coating and all that stuff. You have to build something called as a Faraday cage. A Faraday cage is basically nothing but a place surrounded by metal which reflects radio waves. So in order to ensure that security is easily maintainable, if you use VLC, the light obviously won't escape the room unless there are very clear windows. So there you have security. And there are also militaristic applications when you look at it for submarines, because when you look at underwater communication, it's very difficult for the radio waves to actually penetrate the water at such deep surfaces. But visible light is actually capable of doing this, and in submarines, it will be pretty useful if we can have a PLC communication network between submarines. So having said that, those are the advantages of having a VLC system. Now, how did we come across and make the hardware for this? Because firstly, understand that the hardware for this is not available. An SDR is available to us with antennas and everything. We can just pay money, buy that off the shelf, and then put our code in and use it. Whereas for VLC, at least at this point in time, there is no hardware that will allow us to tinker with it. There are, of course, solutions, one or two solutions, but they are full stack solutions. You won't be able to tinker with any of that. So what we've done is, before I go on to tell exactly what hardware we've used, I'll tell you what changes we've done in the USRP's internal hardware itself before I tell you the actual external hardware, that is the VLC's front end. Now, if you remember, the USRP has two major components. One is the FPGA, followed by your ADCs or your DACs. You have two here, you have two here. Let's just assume this because you have I and Q, again I and Q, followed by which you have your actual RF front end, all of your mixers, local oscillators, you have filters, all of this. Now, anything that comes over here, that is the RF front end portion, is called as the daughter board. And anything that comes over here, which involves the actual FPGA as well as the ADC, is called the motherboard. In a USRP, you can actually take out a daughter board and then replace another daughter board. The motherboard is the main unit of the USRP, which we usually do not take out. If you take it out, it's the same as replacing it as a different USRP. The daughter board, whereas we can actually replace it. So the daughter board that we have used for this particular application, specifically for this application, is a daughter board that does not have any mixers. It does not have any filters. It only has a low pass filter over here. There are no band pass filters. There are no amplifiers. There are no mixers. Nothing is there. You directly take data from the DAC and then give it to this filter. After this, you just have a port, an SMA port. And understand one more thing. in this particular daughter board, it does not follow IQ, meaning there is no addition. You don't take I and Q components. You only take the I and you give it over here. You take the Q and you give it to another port. You have a second port with a second set of local oscillator. You give it to them. Right now, we've done it using a 2920 motherboard. So you only have one I and Q, and each of them go to a particular this thing. So let's say this is the transmit USRP. By the way, I need to use a separate USRP for transmit and a separate USRP for receiving, because the daughter board that's present over here, there are two types in this daughter board. One can only transmit and the other one can only receive. So the I will be given to one SMA port and the Q will be given to another SMA port. Similarly, we have another USRP where a different daughter board, different as in the functionality is still the same, except that this receives instead of transmits. So you have a port here, you have a port here, I, Q. We will only be using one, either I or the Q. In VLC, we do not need both I and Q. We will only be using one of them. So the second USRP will have this receive port, and our signal will be coming in either through one through this and one through this. Now, this is the change that we've done in the USRP hardware. After this, so you might think, okay, fine, the daughter board is inside, but how do we exactly communicate? What is hardware used for communication, right? That is what that hardware that I'm about to talk about now is what will give us the signal in the receive daughter board over here, and will take out the signal from the transmit daughter board over here. Now, like I said, the hardware for the front end, of course, this hardware, the daughter board concept that I showed you is available by NI. That is not a problem at all. The problem arises when we have to actually transmit and receive using visible light. So the front end for that is something that we developed on our own. The concept is pretty simple. For a transmitter, we have two small PCBs where the first PCB takes in the input from the USRP using an SMA port, similar to what you would connect an antenna to. It's exactly the same. In this, what happens is, this power is connected to an SMPS. And an SMPS can provide either, a standard SMPS provides either 5 or 12 volts, but the circuits that we've used inside, some of them require 6 volts. So what we've done is we've taken the 12 volt to another board. We have down converted the voltage to 6 volts. We have some voltage divider circuits over here. And then from here, we give it to this PCB. I'll just name this as PCB TX. So this particular PCB takes in your data and it has a threshold, meaning, let's say I'm sending a sinusoidal signal using my USRP. It has a threshold. So anything above the threshold, it will switch on. So there is an LED over here. Obviously, for visible light communication, we need an LED, right? So for this LED, if the value is above a threshold, it will switch on the LED. If the value goes below the threshold, it will switch off the LED. Since we can't have a negative value over here, it is just on and off, which is why we are using an on-off keying scheme in this. So that is how the transmitter works. The receiver circuit is also actually pretty simple. It receives, there is a photodiode over here that receives whatever light is impinging on it. Again, this particular photodiode has a thresholder on it. It receives the light signal, thresholds it, converts it into, by the way, this is also connected to the SMPS because it needs power. This is converted to the proper signal format, your proper electronic signal format, analog signal format, and then it is sent back to the USRP receiver. When Ajay is showing you the actual system, he'll be showing it to you using a camera, both the LEDs as well as the circuits. At that time, I'll point out which is which. For now, please bear with me. So this is how the signal goes to USRP. This is with respect to the software. With respect to the hardware. Now coming to the software, again, we are trying to transmit only text data at this point. And okay, before I go to that, I just want to give one small piece of information about the hardware itself. Now, the thing is, you can't just use any LED that you get in a normal, electrical shop. You get LEDs for like 5 rupees, 4 rupees, right? You can't use those LEDs simply because the rate at which we want to transmit data is around 200 kilosamples per second, which roughly translates to per second, you will have to switch on or off this particular LED 200K times. If I have to put that into perspective, that is basically 2 lakh times per second. I'll have to switch this on and off, which is actually a pretty high value. The LEDs that you buy off the shelf, or rather, I shouldn't use the word off the shelf, I should use the word, the ones that you get in the normal electrical shops, will definitely not be able to cope up with this particular speed. So what we do is we actually get a proper LED which will be able to, get this rate, it will be able to react to this rate. And the photodiode as well, the photodiode you'll have to select based on what is the angle in which it can receive light. Meaning, if light is coming like this photodiode won't be able to receive it. The grade of the photodiode, that should be good, and the angle that it covers should be good. Typically, the one that we have bought covers about, if I'm not wrong, 15 degrees, if I'm not wrong. But the advantage is that this particular LED actually gives out light in a lot of directions. So it'll actually come within the range of this photodiode, not to worry about the photodiode not receiving the signal. Right, that was with respect to the hardware. Now moving on to the software. We, again, like I said, transmit text data. And since we already had a framework for CISO which used radio waves, we wanted to just modify that because that lessens our work at this point. We wanted to simply modify that and then show it to you. So again, the steps are the same. Text to bits. We don't do channel encoding over here because at this point we thought that was not necessary. I'll tell you why as well. Post which we directly go to packetization. The reason is because at this point, we do not need any modulation. Modulation, as in your proper digital modulation schemes, are not required because your LED is only capable of 2 states, off and on. So what we do is we directly go to packetization. Again, sync. Training we do not put, we do not require any channel estimation or equalization. Again, I'll tell you why. But before that, we put guard, sync, and then your actual data, followed by again guard. It's very simple. We've removed one component that we did in the original CISO. Now, after this, we do something called as a line coding scheme, which is basically what you might know. The line coding scheme that we are using over here is Manchester. And there is a reason behind this. So let's say instead of sending to a Manchester, I just do a normal on-off keying. And by on-off, I mean, let's just say, let's do a return to 0. Meaning if it's a 1, it will stay over here. And if it's a 0, it will go back. Now, the problem that occurs with this will definitely work, as in the signal will definitely be captured. But the problem is, let's say, I switch on my transmitter for 3 seconds, which is basically this duration, and then I switch it off. This is your off state. Meaning the transmitter is no longer transmitting anything. Now you can notice that the 0 during your transmission state is the same as the off during the off state. Meaning the receiver will not understand if you're not transmitting or if you're just sending a bunch of zeros, and it will just decode that. Now, we really don't want that to happen, because when that gets decoded, you just get gibberish, you get noise, and not something that we would like to display. Like imagine having a WhatsApp message where you just keep getting gibberish because nobody's sending anything. We don't want that, right? So what we do instead is we do a Manchester coding where a bit, so one bit is represented by 2 different levels in your signal that's there. So it's either this or this. And during an off state, since it's always off, this is not considered as a signal at all. This is just considered as an off state, and the receiver understands that this is an off state, which is why we do a Manchester coding at this point. Any doubts for anybody on this, or shall I continue? Okay, post this. Okay, so now I've said Manchester coding, right? Now, if you remember what I took during my CISO session, I mentioned to you that you have your samples coming in like this. So let's say this and this are your samples. Now, if you wanted to do as a pulse shaped waveform, you'll obviously not be able to just use this particular one or just use this particular one and then achieve this shape. I said you will have to append a couple of zeros so that you can use these points to achieve this, basically like this. Right now, similar thing I have to do with my VLC code as well. So what I do at this point is I don't directly go and transmit. So right now, technically speaking, my wave is ready because it doesn't require any further modulation. This is how the signal is supposed to look, maybe like this. My signal is ready. But before I transmit, if I actually look at the what do I call this? If I actually look at the signal that I'm sending out to my ADC, to my USRP, it will be either ones or zeros, right? That is what I'll be sending. So 1 0 0 0. Now I want it to look like this, right? Instead, it will look like this. Because it has to keep going from one state to the other, right? So it will go here, it will then jump to this point. The ADC will make it make this slope like this. After that, it will come back down here, it will come back. Only time that we will have a proper square is when it is either 0 0 or when it is 1 1. Again, this is not what I had in mind. This is not what I intended. I wanted it to be like this. So in order to do that, we follow the same procedure. We take a 1, we add multiple zeros. If there is a 0, even for that, we add multiple zeros. And if it's a 1, what we do is we raise all of these other samples to a 1 value. And we keep these zeros as 0 itself. So what this translates to after this goes through the ADC is, maybe there was a 0 before this. So instead of looking, this is our ideal signal, but obviously we won't get an ideal signal. There'll be some amount of on time and off time. It will look a little bit like this. This is not ideal, but at least it looks like a proper Manchester waveform. You have some amount of on time, obvious to any system that you have, but at least it looks similar to that of a square wave and it doesn't take that triangular shape, which is why we append zeros like we did over there. And in pulse shaping, instead of using a root raised cosine, we use a Manchester coding. That is all with respect to the transmitter. The receiver is also not very complicated. We receive it. So an issue that comes up with when you are dealing with things like VLC, I'll actually open up the receiver code. Okay, this I'll show it to you a little later. Fine. The issue that comes up when you're dealing with the VLC, that is, again, let me iterate, visual light code. In the morning, say, I'm using a visual light code in my house. In the morning, there's a lot of sunlight coming in from the from the window. Now, in the morning, when I transmit via wave, it will look like this. But at night, when there's no light and I'm using very dim lighting, the wave might go like this. Meaning, there is always a DC offset that is present because of your light sources. It can be either an artificial sunlight, natural sunlight, or any artificial lights like an LED bulb or a tube light or any other bulb that you have in your house, any lighting source. Even your mobile phone's brightness, if it is a lot of brightness during a dark time, that can also affect your VLC code. So the problem over here is DC offset. The best way is just basically remove the offset. So how do you remove the offset is take an average of the power throughout. So average of this plus average of this plus average of this, so on and so forth. The average will lie somewhere over here. So you can basically say that I'll keep this as my threshold. Anything going above this, I will consider a 1. Anything going below this, I will consider as a 0. So the very first step in a visual light communication is not matched filtering. We don't need to do matched filtering over here since it's not a radio wave. We do a DC removal in order to ensure that the DC offset is gone. So basically, this is the equivalent of, so actually, no, we don't consider it 0, 1. I'm sorry. So we say that this is this thing, right? This is the threshold. We subtract this waveform with a DC value. So if this is 3, so let's say 3 is the amplitude value that it's offset by. We subtract the entire signal by 3. We say -3. And finally, we get a proper waveform that looks like this. Okay. Now that we are done with DC offset removal, we do a thresholding. So we basically say anything that is greater than 0 is a 1. Anything less than 0 is a 0. And by 0, I mean the amplitude value over here. So in this fashion, we convert our waveform, whatever waveform that we have received, because when you actually use light, this could be 0.2, this could be minus 0.2. Since we are receiving light as such, it can either be, it can also be 1 and minus 1, it can be 0.2 minus 0.2, it can be 0.5 minus 0.5, all depends on what is the intensity of the light. Now, since we want to primarily work with bits, there are no symbols involved here, and since we want to primarily work with bits, we will be converting these values into zeros and ones. After which it's the normal, you do a simple time recovery because you've done an upsampling, you then do a downsampling, and very important, we do a Manchester decoding. And after this, it's all exactly the same as we did before. We detect the frames, and then we say, okay, fine, I will send all of them to be demodulated. And it's all bits in this format. And since you only have two possible values, and since we already do a DC offset removal over here, this is something similar to, you can say that this is kind of sort of like your channel estimation equalization. It's a much, much simpler version. Why this works so well is because you only have two levels. If I have a multi-level system like this, then DC removal probably won't be so simple. But right now we're only using a two-level system, so that issue of channel estimation equalization is inherently taken care of here itself. We don't have to do anything. That is how we're doing this. With that, I'm actually done with the theory of this. There is not much more to talk about it. Ajay, if you're there, could you share your screen and show us also how the layout is?
Yes. My screen is visible, no?
Yeah.
Okay. So this is the transmitter code. So it's similar to that of CISO code. Now we are giving at 1 on 10 kilo rate, and the gain is 0, and 1000 bits will be transmitting. Like in one packet there will be 1000 bits, and we are sample per symbol will be 16 samples per symbol. And this is our text, what we are transmitting right now. So as you can see, our code is running. So I will turn on my webcam and show our. One minute, so I will turn. Okay. Yeah. Are the USRP visible?
Ajay, can you mute yourself in either your phone or this thing? I think you're using two devices, right?
I think. Oh, yeah.
You're not audible now. You're using the same device for both the webcam and the.
Hello?
Yeah, hello.
Echo is not there, no?
No, echo is not there.
Okay. So you have seen the transmitter code. So this is how the setup is done. So this is the LED that will transmit the signal, and this is the setup that we have done. So this is the main board, and above that we have kind of used an child board. You can see here. So this is our USRP, and This is the circuit that we have built, and this will be transmitting. And this is the receiver, so which will be receiving the light signals. And this is connected to another USRP, so which is having similar board to that of transmitter. So, but this will be receiving, and this is our main USRP. And now I'll be showing receiver code. So this is how the receiver code looks, and this is what it is decoded. So this is our text. And as you can see, this is the received signal here on IQ waveform. So when I block the light, you can see there is noise. The noise is there. So when I remove that, you can see a proper signal, so which is a pulse signal, which the receiver is receiving right now.
Right. So as you can see, the waveform that's present over here, it looks a little, it doesn't look like a proper Manchester waveform where you have a little bit of ups and downs. This is simply because of the one is, it could be channel effects. And second thing, when the voltage in a circuit goes from 0 to high, there is a small amount of extra increase that happens in the current. So that could be the cause for your, those small these things that you see, spikes that you see. But again, the spikes are very small, so you won't be able to recognize or realize that there is an error. At least the code, the thresholding happens at a 0 point. So those small errors shouldn't cause us any issues at all. As you can see, we're able to receive the text properly without any issues. Right now, since we are, yeah, sorry, Ajay, continue.
No, yeah, you can continue, Raghavendra.
Okay, right. So right now we're using it at a small rate simply because the LED that we have currently with us is only capable of going to that rate. We are currently in the process of trying to purchase an LED which can go up to actually 1 mega samples per second. The switch on or rate is 1M. In those cases, we'll actually be able to send a lot more data in a lot faster fashion. So we'll actually be able to go up to and transmitting or receiving an image as well to that point. But right now, we wanted to simply do it as a proof of concept. So, which is why we purchased this particular LED and we are going ahead with it. This was phase 1 in our system. Ajay, do you have anything else to add?
No, yeah.
Okay, fine. So this was phase 1. Ajay, you can stop sharing the screen now. Yeah. So this was phase 1. Phase 2 would be to build something called as a open VLC. I'll just take 5 minutes in explaining what that is. Now, an open VLC system, this was actually a paper written by that particular, this thing that I told you about, the university that I told you about. It's called IMDA Networks Institute. So it's in Spain, and these guys have actually built a system that is very cheap, relatively cheap system. So what they do is they don't just emulate the physical layer, they go up to the network layer. So what they've done is they have taken 2 laptops, one that acts as the transmitter and the other that acts as a receiver. They want to do a video transmission. What they do in this case is they have another piece of hardware that is like a computer called as a Beagle Bone Black. If you want to understand what a Beagle Bone Black is, it's almost, you can compare it to that of a Raspberry Pi. It basically has an operating system sitting in it. You'll be able to run an operating system. If you can connect a monitor to it, you can actually view anything that's happening inside. You can code inside, anything you can do. So they have 2 sets of BeagleBone Blacks. They chose a BeagleBone Black because that's a more industrialized version of Raspberry Pi. Actually, it's a different company itself, but industries prefer BeagleBone Blacks to Raspberry Pis. There are, of course, other hardware advantages as well. I don't want to get into that right now. So what they do is these BeagleBone Blacks, like Arduinos and Raspberry Pi, they have pins over here, input and output pins. They connect their own proprietary your visible light front end, VLC front end, optical front end to this, the green part that you can see on top over here. They connect this and they stream data from one place to the other. Now, how they've actually done it is they've used a HTTP protocol. Since it's a network layer, we have to now talk in terms of protocols and not just, in terms of signal strength, etc. So they've used a HTTP protocol where one particular laptop accesses the video server, the other accesses the video client. Now you may ask, why do we have a BeagleBone Black, which is basically a computer, if you already have two laptops over here? The reasoning is simple. You want to reduce the amount of load that you put on either your laptop or your BeagleBone Black. The duties are divided among them. Now this has only the network layer. They've actually mentioned this very clearly in their website. I can show it to you. Right. So you can see over here, this is from their website. They have a TCA is basically their transmitter. TIA is basically the receiver, the one that has your photodiode. They've made their own PLC firmware. It's just a piece of software that they program. Again, they call it PRU, Programmable Real-Time Units. That firmware is running on your BeagleBone Black. The box that you see over here is the BeagleBone Black. So the BeagleBone Black is responsible for running the physical and the MAC layer. The network layer and transport layer are taken care of by the laptop, but are not visible to the user. Only thing user can do is view the application layer. The application layer will have the video information. It will actually stream the video. Now, how they've done it is actually pretty smart. They use a USB to Ethernet, virtual Ethernet port using a USB connection. They connect the laptop to the BeagleBone Black using a USB. The BeagleBone Black does all of the MAC and physical layer processes, sends the video data through the air. The receiver again receives it. It takes it back to the receiver client. Now you see something called as back channel over here. Like I said the first time, there are a lot of systems that use your retransmission architecture, especially one that involves something like network layer and MAC layer. So what they do is they actually connect the LAN ports of both the video client, that is the receiver, as well as the video server, that is the transmitter. So basically what it says is the actual data that you want to send is sent through this. If there is any control signals to be sent, for example, if there are acknowledgements where the video client says, okay, fine, I've received packet number 2, I have received packet number 3, all of the acknowledgements and control signals, all of that takes place through a TCP/IP protocol. If you want, I can just, they actually have a video on their website as well. I can just show it to you. By the way, the website is called as OpenVLC. You can access it to see it. I'll just show you a demo of how their system works. We actually hope to go to this point at, like this is what we're trying to do right now to achieve this. Ma'am, please let me know if the audio is audible to all of you.
Yes, you are audible. Raghavendra? Yes, ma'am. Yeah, if you're talking about this video ka audio, it's not. Oh, okay. Okay, then I'll just show you the video. I'll walk you through it. So this is this is something called as, they call it as a cape. Typically, if you try to put this on any Arduino or any your Raspberry Pi, you call this as a shield. So this is something that they have made on their own. You can see that this contains an LED, which will be, sorry, this is the photodiode. This is the photodiode that receives your light. And this is the LED. The LED is actually housed inside. This is a magnifier piece of this thing equipment that they have over here. It's just a glass that magnifies it. And this is they've custom made this on their own. And they'll be fitting this onto the BeagleBone Black that I mentioned before. Right. So BeagleBone Black takes care of all the MAC and physical layer processing. So they just insert it onto the BeagleBone Black. They don't have to do anything else. There's no wiring, messy wiring involved. Everything is done on the PCB itself. You can see that they have connected a USB port from here. There's an USB port on the system also. So one of the devices, and the light that they use is actually pretty powerful. The LED that they have is very powerful. So they're actually able to cover a distance of 3 meters with this. And you can see the blue color wire over here. That wire is what is used for your
back channel communication for all of your acknowledgements and control signals. The left, one on the left is transmitter and one on the right is receiver. And they actually have some application and transport layer, all of that running in the systems. And everything is Ubuntu software. Since it's open source and easier to use in terms of development, they use an Ubuntu software. So virtual Ethernet connection through USB is how the BeagleBone Black is connected to the laptop. Since I said we use HTTP and TCP/IP protocols, it's better to use these as a virtual LANs so that it will be part of the same network. So you can see that light. So these guys actually do it at a very fast rate. Like I said, they do it at 1 mega samples per second. So that for that reason, you actually won't be able to see the blinking of the LED. In fact, even in our system, if you see, since 110K, which is basically be transmitted at around 1 lakh blinks per second, so you won't actually be able to see it with your naked eye. But there is data actually coming in, and you see the video that you're seeing here is being streamed from the first laptop, the laptop on the left. And they actually have a buffering system similar to YouTube, where if for some reason in the middle for a couple of seconds the transmission stops, there is a buffer present inside the receiver over here, which will keep on running the video. It's similar to YouTube. Now you can see that this much is buffered in YouTube. Now if I switch off my internet also, I'll be able to play and see this. They've employed a similar mechanism over there. So you see the video is still running because of the buffer. And now the buffer will be emptied now. And then the video stops at one point. And then it continues again. So they've actually built this, and in fact an entire Li-Fi stack. So a Li-Fi is a technology that you use instead of Wi-Fi. You basically use light in order to transmit information. So it's as simple as plugging in a bulb, and then you'll be able to see YouTube, watch Instagram, go on WhatsApp, and then do your communications. So with that, I am done for today's session. That is what we wanted to talk to you about VLC, and then show you what we have done with respect to visible light communication and what we hope to do in the future as well. If you have any doubts at all for Ajay or me, please go ahead.
Thank you, Raghavendra. Thank you so much.
Thank you, ma'am.
Thank you. Thank you, Ajay. Yeah, it was a nice journey to go through all the devices on which you people are working, and he also showed the the entire lab setup. That was very interesting. Thank you so much.
Thank you, ma'am.
Yes, dear participants, we are done with the last session of this Friday's FTP. So let us move on to the very interesting component of this FTP, that is the validatory function. Let me share the slides. Madam. Hello everybody. I welcome all of you to the last component, that is the validatory function. I have a few slides which are repeating. Yes. So we started this event in cooperation with the Avagadi Systems Private Limited Company, who are the pioneer workers in the domain of software defined radio. And the event was scheduled for these 5 days. Yeah, this is how we had planned the things. And I can say that 95% of the times we could stick on to the timing and the other schedules. Only on the last day, because of some issues, we could exchange, but we could not skip any of these topics. We could cover all this completely. Yeah, regarding the number of registered participants, this is what is the graph. And we have almost people from 7 to 8 states of India. And a few clippings I have taken, starting from the first day, where the speakers went on discussing about the USRPs, RIOs, and the SDR architectures, and they also demonstrated few of the simulations in the VI platform. These are again to add to the first slide, few more things. Yes. So at the end, the CEO of Avagade Systems, who presented some insights of the research areas which are there in the SDR domain. And he also demonstrated the lab setup that is available there. So with all this being successfully conducted, it would not have been possible with the support of all these people whom I have mentioned here. I personally want to thank the sponsors of VGST, who have kept some fund for organizing such kind of events under the category of faculty development program. And I would like to thank our Vice Chancellor, Sir, Dr. Ashok Shettar, who is always supporting all our faculty for conducting such kind of events. And we also have our Registrar, Sir, Dr. NH Ayachit, Sir, and HOS Dr. Nalini C. Iyer ma'am, who always encourages the set of events of this kind to happen in the university as well as in the department. And I want to personally thank all the resource persons from IITs and other institutions, NITs, who took their precious time in delivering the contents which are very valuable and helpful for all the other participants. And I'm very much thankful for the industry partners, a team of engineers from Avagadi Systems. To mention the names, we have Raghavendra, Ajay, and Murthy today, who took all the say half the session, and Nilutpal Chaudhary in the front end. In the back end, we have Amal K. Sebastian, who is taking care of scheduling all these events and the topics, and he is the core person in arranging all these speakers also. I thank all these people of Avagadi Systems. And I personally want to thank all the participants for their active present say the active participation, as well as they could interact with all the resource persons and get their doubts clarified. And that was very good component of this program. And finally, I would like to thank the organizing committee members. Along with me, we have two more faculty members, Professor Vishal Patan Shetty and Professor Anil K. Kapoor, who were helping me in organizing every event, every small activity of this particular event. And at the end, I would like to thank all the other supporting people who made this event happen and made it a successful event. And I thank all of you. And at the end, I would like to request all of you to give the feedback on this event. I will stop presenting now. Yes. request